Okay, class, welcome back. We are tackling chapter 11. We're going to learn about gases. Okay, this is the beginning of exam 4 material. So before we start talking about gases, it's really important for you to understand what pressure is. So pressure is the force exerted per unit area by a gas molecule, right, as they collide with the surfaces and each other. Right, so the surfaces around them and each other. So just as a ball exerts a force when it's bounced up against a wall, a molecule of gas also exerts a force when it collides with a surface. The result of many of these collisions is pressure. So the stronger the collisions, the more the collisions, the greater the pressure. On Earth and at sea level, the gas molecules in our atmosphere exert an average pressure of 101,325 newtons per meter squared, or in English units, 14.7 pounds per square inch, psi. So in order to now that we know what pressure is, all right, we can talk about kinetic molecular theory, which is a theory for understanding the behavior of gases, okay? This model predicts the correct behavior of gases for most gases under many conditions, okay? Like other models, this theory is not perfect and it does break down under certain conditions, but we're going to focus on the conditions where it works well. So essentially, this is kinetic molecular theory. There we go. So according to this theory, a gas is a collection of particles in constant straight line motion. Gas particles do not attract or repel each other. They do not interact. There's a lot of space between gas particles compared to the size of the particles. There's a lot of space between gas particles compared with the size of the particles themselves. So there's a lot more room, right? There's a ton of room in between gas, or a lot of space in between gas molecules, okay? And they're also very small. This is essentially why we can assume that they don't interact, because there's so much room between gas particles. So the average kinetic energy, energy due to motion, right? It's kinetic energy of gas particles. We have to take the average, right? Always, because we can't sit there and evaluate each individual kinetic energy of each individual gas particle. So the average of its kinetic energy is proportional to the temperature of Kelvin, of gas in units. Oh my gosh, temperature of gas in kelvins. This means that as temperature increases, particles move faster and therefore collide more, they have more energy, they also have more pressure, essentially. So here's a little pictorial representation of kinetic molecular theory. Again, gas particles move in constant motion until they hit the sides of the container or each other. There are no attraction or repulsion forces between particles, even though they may interact when they collide. They just interact like two billiard balls or two, pool balls when they hit, right? They just bounce off each other quickly and then go in opposite directions. There's a ton of space between the particles compared to the size of the particles themselves, and the speed of the particles increases with increasing temperature, all right? So that is kinetic molecular theory. So kinetic molecular theory also allows us to it's very consistent with the properties of gases that we've been able to observe. First, we know that gases are compressible. We know that gases assume the shape and volume of their container, and we also know that gases have low densities compared to liquids, their liquid phases and their solid phases. So again, this is why kinetic molecular theory correctly describes the fact that gases are compressible. That is because there's so much empty space between gas particles that we can easily compress them down. Liquids are not compressible, right? Because there's so little space between the liquid particles that we can't push down, we can't compress the liquid any further. A gas always assumes the shape of its container. This is because the attraction forces between molecules are negligible, right? We can basically just ignore them. And since particles are in constant motion, a gas expands to fill its container and it also expands to take the shape of its container as well. Gases also have low densities, so essentially, this is because in comparison with solids and liquids of the same compound, there's so much empty space between the atoms or molecules in a gas. So here's an example. If you have a can of soda, right, we obviously know it fills one 12-ounce can. If we were to take that liquid and convert it to gas, the volume that it would take up is equal to that of 1,700 cans of soda, right? Another example, so that's a huge difference in density, right? Another example, so steam at 1 atm, steam is liquid water, right? Or, sorry, it's gaseous water, and we can only, that's at 100 degrees Celsius, is about, this is how small it is. The density of steam at 1 atm is 0.0006 grams per centimeter cubed, where the density of liquid water at room temperature is 1 gram per 1 milliliter, or 1 gram per milliliter, right? So that's a big difference. So you can see that the density of water in its vapor form is much lower than water in its liquid form. So, again, pressure is the result of constant molecular collisions. And these collisions are between the atoms or molecules in a gas and the surfaces around them. Because of pressure, we can drink from a straw, inflate basketballs, move air in and out of our lungs. All right, and we'll talk about the drinking of the straws in a second. So variation in pressure in Earth's atmosphere creates wind changes, helps us predict weather. It also pressures all around us and even inside of us. And a really good example is when you are driving in the mountains and you want to pop your ears. That's because the outside pressure is lower than the pressure inside of your ear canal, and that causes your eardrum to bulge out, because essentially those pressures want to equalize, and that pain results from, in your head, in your ears, results from your eardrum bulging. And the only way to get rid of that pain is to have the pressures equalize within your ear canal and outside of your ear canal. So the pressure exerted by a gas sample is defined as the force per unit area that results from the collisions of gas particles with surrounding surfaces. Again, pressure is also equal to force over area. Okay. So it's also the pressure exerted by a gas depends on several factors, including the number of gas particles in a given volume. Okay, so you can also think about the fact that pressure is going to increase if we have greater, like the same container, the same volume of container, right, as we have here and here. But if we have more gas molecules in the container, we're going to have higher pressure. That's because compared to fewer gas particles, there are more collisions, right? There are more collisions against the surface of the container. There are more collisions between gas particles. And these collisions are pressure, so if you have more collisions, you're going to have higher pressure. The simplest unit of pressure is the atmosphere, which is 1 atm. It's the average pressure at sea level. The SI unit of pressure is the Pascal, and it's defined as 1 Newton per square meter. So there's this. And you'll just really fast, 1 atm equals 101,325 pascals. So Pascal is a much smaller unit of pressure than atm. Another unit of pressure is millimeter mercury, all right? And it originates from how pressure was derived measured with a barometer. So bear with me, and I'm going to talk about this really fast. So you have a glass tube that's under a vacuum, meaning that we've removed, I'll say very low pressure, right? since it's under vacuum, we have essentially removed all the gas molecules, right, within this container. So this is essentially just empty space and nothing else. And then we take this tube that is under vacuum and we put it in a dish full of liquid mercury. All right. So we have this. What we've already created is we've created this pressure difference where the pressure inside the tube is, sorry, that's kind of funky. Let me just make sure. Pressure inside the tube is much smaller than the pressure outside of the tube, okay? So this pressure difference, right? This is this kind of same thing, but opposite when I was talking about the eardrum situation. So this pressure difference, where the atmospheric pressure is greater, causes a force, right? This force, there's a certain amount of force that's pushing on the surface of the liquid mercury, right? It pushes on the surface of the liquid mercury, and essentially what it does is it pushes the liquid mercury up the tube, right? Because there's essentially, this is under vacuum, there's no pressure up here. So this force that's exerted upon the surface of the mercury pushes the liquid mercury up the tube. And it turns out at atmospheric pressure, right? We've standardized it then. At 1 atm, the height of the mercury within the tube is 760 millimeters. So we can actually sit back and relate ATM. So that's why we've standardized this unit, right? 760 millimeter mercury is equal to 1 ATM. Also, 1 ATM is equal to 29.92 inches mercury, right? Because, so again, when at pressure of 1 ATM, right, the liquid mercury will be pushed up the tube at a height of 760 millimeters, or 29.92 inches. So that's essentially where we get this from, okay? This is actually the same type of mechanism behind why we're able to drink out of a straw, right? If you can imagine that you would never drink liquid mercury, just to let you know, but let's say that this is water, right? And this is a straw, and your mouth is up here, and then essentially what you do is you remove the pressure, right, by sucking out all the gas particles in the straw, and what ends up happening is the atmosphere pushes down on the surface of the liquid, and then the liquid travels up the straw, okay? And then it reaches your mouth. So that's how we are able to drink from a straw using pressure. So since 1 atm of pressure pushes the column of mercury in a barometer to a height of 760 millimeters, 1 atm is equal to 760 millimeter mercury. Millimeter mercury is also called a torr. All right, so 1 millimeter mercury is equal to 1 torr. Other common units of pressure include inches mercury, right, pounds per square inch. So again, 1 atm is equal to 29.92 inches mercury, and 1 atm is equal to 14.7 psi. You will be asked to convert between units of pressure. You will be given something like this in an exam, so you just need to know how to convert. So let's go ahead and let's do this problem really fast. So say we want to convert 311 atm to millimeter mercury. So what we're going to do is we're going to say we know already that 1 atm is equal to 760 millimeter mercury. So, probably plug it in our calculator, ATM cancels, answer is left in millimeter mercury. And turns out, this is the whole problem again. Just worked it out for you up there. There it is. And 236. So again, 0.311 ATM multiplied by 760, and that gives us 236 millimeter mercury. Okay, so now that we know about kinetic molecular theory, we understand what pressure is. It's the force exerted from gas molecules colliding with a surface. That surface can be your body, it can be the ground, it could be the surface of a container that's holding a gas, it could be the surface of a liquid that pushes pushes the liquid up a straw. All right, and since we know kinetic molecular theory, we also know units of pressure. We know how to convert them, and we even know where millimeter mercury was derived from. Now we can start talking about laws for gases. Okay, so first we're talking about Boyle's law, which relates pressure and volume. So the relationship between gas properties are described by gas laws. Okay, so the relationship between volume and pressure was discovered by Robert Boyle, and it's really important for you to understand first that this law in particular assumes constant temperature and constant number of gas particles. Okay, so we can also say constant moles. All right, so constant number of gas molecules. And Boyle's law states that the volume of a gas and its pressure are inversely proportional. Okay, so this is the volume, and then you have this little symbol right here. This means proportional to, and then 1 over P. So essentially, as volume remember, it's inversely proportional, so as volume increases, right, pressure will decrease. So you can see here's just a little pictorial representation of Boyle's law. On the left-hand side, we have a volume of 1 liter and a pressure of 1 atm. Same 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 gas molecules, all right, at 20, let's say 25, so 10 molecules, I'll say 10 moles. 10 moles at 25 degrees Celsius, right? And then the same amount of moles at 25 degrees Celsius, right, over here. But what we did was we halved the volume, right? So we halved the volume. So volume decreased. So volume decreases, we should assume, according to Boyle's law, that pressure will increase. And turns out pressure increased from 1 atm to 2 atm. And you can just see why that makes sense, right? When we compress the gas molecules, the force that they exert against their surface is going to be greater than the non-compressed version. Here's another example, or the same example, and just kind of invoking kinetic molecular theory into this explanation, right? So kinetic molecular theory explains that the observed change in pressure, if the volume of a gas sample is decreased, right, the same number of gas particles is crowded into a smaller volume. So again, the same number of gas molecules, causing more collisions with the walls of the container and therefore increasing the pressure. So we're not going to, so Boyle's law is represented like this, okay, in our equations. P1 V1 equals P2 V2, where P1 is the initial pressure, right? V1 is going to be the initial volume, and then P2 is the final pressure, and V2 is the final volume. And just like our M1 V1 equals M2 V2 for our molarity dilutions situation, we can oftentimes will be given, let's say, 3 out of the 4 variables, and then you'll have to rearrange and solve for the 4th. And so the way that we would set this up, though, or the way that we would look at this problem or equation is we would say P1 is going to be equal to 1 liter, and that's multiplied, to put everything in parentheses, so 1 liter, right, and that's multiplied by V1, which is 1 ATM, whoops, is equal to, down for more room, is equal to 0.5 liters, which is our V2 multiplied by 2 ATM. Okay, and again, this is at constant temperature and number of moles. So here's a problem. A cylinder equipped with a movable piston has an applied pressure of 4 ATM and a volume of 6 liters. What is the volume of the cylinder if the applied pressure is decreased to 1 ATM? All right, so first, again, we're going to use P1 V1 equals P2 V2. And what we're going to do off to the side is we are going to isolate our variables. All right, so P1 is 4 ATM. V1 is equal to 6 liters. And then finally, P2, well not finally, P2 is equal to 1 ATM. And then V2, we don't know. All right, but before we even do anything here, let's just take a look at what these numbers are. All right, we know that for Boyle's law, as pressure increases, volume decreases. So we were given both variables of pressure, and this is the pressure initial, and this is the pressure final, and you'll notice that pressure went down. All right, it went from 4 ATM to 1 ATM. So if pressure went down, we should assume that volume, according to Boyle's law, will go up, right? So we have to the first thing we're going to have to do is let's figure out if that's right, and let's rearrange and solve for V2. So it's going to be V2 equals P1 V1 over P2. Okay, and then I'm going to put P1, which is 4.0 ATM. V1 is going to be 6.0 liters, and then our P2 is going to be 1 ATM. So it's really important for you, if you are given different units, right, that you have to have the same unit, right? Pressure units have to be equal, and volume units have to be the same, all right? So before we plug this in our calculator, you'll see that ATM cancels, and our answer is left in liters, which is what we want. So we put equals right there, and it looks like, oh, I don't have to, 24 liters, okay? So that is our final volume is 24 liters, and turns out, is this correct? And the answer is 6 liters greater than 24? No, it's not. 24 is greater than 6, so obviously this relationship worked out. So when you start working these problems, it's a good idea to start implementing, some thought into what the answer should be. All right, does the answer make sense? According to Boyle's law, we know that this is the relationship, so we should expect our volume to increase, and we did. Okay, so this is just the same thing. So, a snorkeler takes a syringe filled with 16 mils of air from the surface where the pressure is 1 ATM. Okay, so again, this is still P1 V1 equals P2 V2. Right? P1 already, I know, is 1 ATM. V1 is equal to 16 mils. The volume of the air in the syringe so the pressure, so the syringe is taken to an unknown depth. The volume of air in the syringe has decreased, right? So V2 has decreased from 16 mils to 7.5, and it's asking for the new pressure, right? So again, pressure should increase because volume decreased. So we have to rearrange P1 V1 equals P2 V2 to solve for P2. So P1 V1 over V2 equals P2. And then we're going to plug in our variables. So we have 1.0 ATM. Actually, I'm going to do this over here. 1.0 ATM multiplied by 16 ml over 7.5 ml. And again, I have all my units matching, so I have ml. Sorry, my kid's sleeping and my dog's barking and I don't want him to wake up. Okay. So P2 is going to equal 16 divided by 7.5, and 2 sig figs, so we're looking at 2.1 ATM. So that is the pressure at this depth right here. If the pressure increases by an additional 1 ATM for every 10 meters of depth, how deep is the snorkeler? So we know that we increased from 1 ATM, so we'll say P is P. It's the change in P. So the change in P, so P final was 2.1 ATM, right? And P initial was just 1 ATM. So our delta P is 1.1 ATM. So if we take 1.1 ATM, and we know that for every 1 ATM, for every 10 meters, we increase our pressure by 1 ATM, right? So we can say for every 1 ATM, right, we can use that as a conversion factor, 10 meter. And we can use this to convert from ATM to meters, which is what we want. And so 1.1 obviously multiplied by 10, oops, is 11. All right, so the snorkeler is 11 meters deep. Okay, so now we're going to talk about Charles' Law really fast, and then we're going to stop here. This is going to be the first portion of, well, actually it might be 3. We're probably going to have 3 to 4 lectures on this. So this will be we'll finish Charles' Law, and then we'll stop here. So Charles' Law is another law that represents or gives you a relationship between volume and temperature. So, nice question you might want to ask yourself is, why does hot air rise? And again, this has to do with Charles' Law. So hot air rises because the volume of a gas at a constant pressure, so this is important, constant pressure and constant number of moles increases with increasing temperature. So again, we have as volume increases, so does temperature. Or another way to put it, the way that I like to think of it, right? Because I think of temperature being the independent variable. As temperature increases, volume increases at constant pressure and number of moles. So as long as the amount of gas, and therefore its mass, remains constant, all right, so we're still trying to think about why does a hot air balloon, right? Why does hot air rise? And we know just from, just in our chemistry lab, if we mix 2 liquids together and if they have 2 different densities, the more dense liquid is going to sink to the bottom if they don't mix together at all, like an oil and a water, right? Water's more dense than oil a lot of times. So water will sink to the bottom, oil will raise to the top. All right, so the more dense substance will always be at the bottom. All right, so if we increase the temperature, volume is going to increase of a gas. And if volume, so remember the density of a gas, right? If volume increases, but the mass stays the same, the new density is going to be smaller because we're dividing by a larger denominator, all right? So the density of the gas will go down, and therefore, since the density of the gas goes down, the gas will rise, all right? A lower density gas floats in a higher density gas, or a lower density floats in a higher density gas, just as wood floats in water. Okay. So, again, hot air balloon, heating the air in a balloon makes it expand, right? Heating the air in the balloon makes it expand, and as the volume occupied by the hot air increases, its density decreases, allowing the balloon to float in the cooler, denser air that surrounds it. Here's another example. We have, and this is actually a pretty cool thing that we're going to talk about in a second. Imagine you have a balloon, same balloon. It's got a certain amount of gas particles in it, right? Stays constant. You put that balloon in ice water, and you're decreasing the temperature, so the volume of the balloon is going to decrease as well. You put that same balloon in hot or boiling water, the volume of that balloon is going to increase with the temperature. And here's an example over here. You can see that as temperature increases, volume decreases. You will also see that this data, right, has been extrapolated all the way down to 0. And if you zoom in really closely, you can see that at 0, so at 0, well, we should say not at 0, we should say at negative 273 degrees Celsius, okay, we have the volume of a gas equals 0, right, which is kind of weird if you think about it. And that anything below 273, which is right here, volume is now negative, which is theoretically impossible. So, we can predict an important property of matter by extending the line in our plot backwards from the lowest measured point. This is called extrapolation, what I just mentioned. Our extrapolated line shows that the gas should have a 0 volume at negative 273, which corresponds to 0 Kelvin, which is the coldest possible temperature. The extrapolated line also shows that below 273, our gas would have a negative volume, which is physically impossible. For this reason, we refer to 0K as absolute 0. Colder temperatures do not exist. They don't exist because it would be physically impossible to have a gas with a negative volume. It's also pretty hard to have a gas with 0 volume too, which is probably another reason why we can't get it that cold. So again, Charles' law states volume and temperature, again, first of all, are directly proportional. As volume increases, so does temperature. Here's that relationship right here. And this always assumes constant pressure and constant amount of gas, or constant moles. So this is all very, very straightforward. When the temperature of a gas sample is doubled, so does its volume. All right, so long story short, you can read through this. I'm not going to read it all to you. It's very basic and straightforward. But if the temperature of a gas sample is increased, the gas particles move faster, And if the pressure is to remain constant, the volume must increase. And we pull this again from the kinetic molecular theory, and we know that there is a relationship between temperature and volume of a gas, right? We know that because we know that the average kinetic motion, right, or the average kinetic energy of a gas is directly related to its temperature. If we heat up the gas, it's going to have more molecular motion. More molecular motion, right, increases the pressure. But if we have constant pressure, the volume must increase. Same thing. This is, again, just driving this point home with the balloons. But I already talked about it, so I'm just going to skip it. So Charles' law, you'll notice here, this is remember, Boyle's law was P1 V1 equals P2 V2, right? And, Boyle's law I have an old iPad, so it doesn't have very good palm recognition. I'm going to just do this as what I'm going to do. Sorry, bear with me. Here we go. This is ugly. So really fast, I just want to sit back and say, you know that Boyle's law says that pressure and volume are, as volume goes up, pressure goes down. They're indirectly proportional to one another. So the relationship that the equation that we use is P1 V1 equals P2 V2. Charles' law is different because Charles' law has volume directly proportional to temperature. All right? It's different than one volume proportional to 1 over P. Its volume is directly proportional. So since it's directly proportional, this is what this is the equation that we're going to use in these types of problems, all right? So I want you to notice the difference, right? I want you to notice how indirectly proportional we have this like P1 pressure multiplied by volume. And here we have, if it's directly proportional, we have volume divided by temperature, okay? So it's also really important to mention that the pressure and the amount of gas are constant, okay, in Charles' law. So the pressure and the amount of gas are constant. And all temperatures must be expressed in Kelvin. So here's an example. Again, we're going to do Charles' law, which is V1 over T1 equals V2 over T2. Sorry, that's messy. A sample of gas has a volume of 280 liters. So I'm going to put volume V1 equals, V1 equals 280, 2.80 liters at an unknown temperature. So already I'm going to say, all right, well, T1 is a big When the sample is submerged in ice water at a temperature of 0 degrees Celsius, its volume decreases to 2.57 liters. So V2 goes to 2.57, and T2 was given as 0 degrees Celsius. Its volume decreases, right? What is the initial temperature in Kelvin at constant pressure, right? So here's the big thing is you got to remember how to convert from, I will give it to you, I'll let you know, but I'll just go ahead and say T2, we're going to convert to Kelvin, equals 0 degrees Celsius plus 273.15, right? 273.15 Kelvin. Okay, whatever conversion I give you for Kelvin, whether it's 273.15 or just 273, whatever I give you on the exam, that's the one that you're going to use. Okay, so I can go ahead and now say, all right, it's 273.15. All right, so we need to rearrange this. We need to rearrange V1 over T1 equals V2 over T2. We need to rearrange this to solve for T1. So how are we going to do that? We got to do a little bit of algebra, okay? And I'll take you through it one time, step by step. So again, we need to isolate T1. So what we're going to have to do is first get it out of the denominator, right? So you can multiply both sides by T1. All right, T1 cancels. So that leaves us with V1 equals V2 multiplied by T1 over T2. So again, we still have to isolate T1. So the way that you're going to do it is you're going to then I was trying to think if I could. Then you're going to multiply both sides by the reciprocal of this. Or you can do it one by one. It doesn't necessarily matter. You can multiply both sides by T2, right, to give you T2 V1 equals, let's take it through you step by step. T2 V1 equals V2 T1, right? And then again, you can just divide both sides by V2 to give you T1 equals T2 V1 over V2. Okay? So again, what did I do? Up here, I multiplied both sides by T2. Okay, this canceled. Right, and that gave me T2 multiplied by V1 equals V2 by T1. And then what I did is I divided both sides by V2 to get this to cancel. There we go. Okay, and then this is what we have. All right, so you're just going to have to do a little bit of algebra. No big deal. You guys can do it. So I have this set up. All right, so what you're going to do is you're going to then take this amount, all of these guys, and you're going to plug in your variables. Now, since I don't have enough room, I'm just going to go ahead and just move down here. Right, and we have T1, same thing, T1 equals V1 times T2 over V1. It's the same thing as saying, me writing it, T1 equals V1 T2 over V2. It's the same thing, all right? So again, we're going to plug in our variables. I had them isolated or assigned up at the previous slide, but I'll just show you really fast. V1 is going to be 280 liters. Right. T2, I have 273. I had 273.15. That's not a big deal. Doesn't matter because we're going to drop those sig figs anyway. And 2.57 liters. Okay, so liters cancel. Answer's left in Kelvin, which is what we want. And turns out we have our new volume, or I'm sorry, our new temperature, T1 equals 297 Kelvin, okay? So, again, it's really also, is there anything else I need to mention? Oh, they just converted it back to Celsius down here. That's not that big of a deal. That is not that big of a deal. So again, what we had to do what is the initial temperature? Oops, sorry. We needed to find the initial temperature in Kelvin. All right. So this is something that your book tells you as well. To distinguish between the two temperature scales, use T for temperature, lowercase t for Celsius and big T for temperature in Kelvin. Just make sure that you write the units for everything. I think that's really, 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 really important. So again, remember, T2 was, right? T2 was 273.15. So our final volume is going to be 297 K. And if you needed to convert that back to Celsius, you would do that here. But this is what I want. All right, we'll do one more. A gas cylinder with a movable piston has an initial volume of 88.2 liters, milliliters, and is heated from 35 degrees C to 55 degrees C. What is the final volume? So it is heated from T1 equals 35 to T2, which is 155. And then what is the final volume? So the first thing we have to do is we have to convert these guys to Kelvin. So 273 plus 273. So we have 8. So 308. Yes, that's right. 308K. And we have 8, 12, 428K. I am going to double check that just to make sure, because you know how math in head works when I am trying to lecture. 273 and 155 plus 273, 428. Okay, so now I have my new temperatures. I have, remember, it is V1 over T1, right? Temperatures on the bottom equals V2 over T2. And we need to rearrange and solve for V2, so that's pretty straightforward. So we just need to multiply both sides by T2. And that's going to give us V2 equals T2 multiplied by V1 over T1. Okay, then I'm going to plug in my variables. All right, so I have for T2, I have 428K multiplied by V1, which is 88.2 ml. Over T1, which was 308 Kelvin. Okay, so Kelvin cancel. Answers left in milliliters, which is what I want. So I have 428 multiplied by 88.2 divided by 308. And I have V2 equals 3 sig figs, so 123 ml. Okay? When we come back, we will talk about the combined gas law. So this is ending lecture 1 of probably 3 or 4, I'm not sure, but definitely lecture 1 of gases, chapter 11.